Okay, so anyways, separable equations is what we're going to talk about. And it's more about differential equations. This is going to be the last section in chapter 9 that we cover. And then tomorrow we'll be into chapter 10. But anyways, so here again, we have a differential equation that would be solved. Now, normally what you've seen so far about solving differential equations is you've seen things like dy equals some expression, dy dx equals some expression, but there's only x's over here. In this case, there's a y right there. It's a square root of y on this side of the equation opposite the dy dx. So you can't just integrate this somehow because there's this y in there. Okay, if everything was x's, then maybe you'd have a chance of integrating it and then just getting the answer, but that's not the case here. But this is what we call separable. So we're kind of lucky here in this regards. And what happens is you treat this dx as like you treat this as a fraction, okay? So what that means is, and right now I'm just gonna change this. Well, this can go over here, and the dx goes over here. Okay, so it's kind of like it's just like some algebra, as if this was a fraction, even though it's not really a fraction. But as far as what we're doing here, it basically, you can treat it as such. And take the dx over here, and then take the square root over there, the square root of y over there. Okay, and then what you do is, the idea is, over here we have only y's and a dy, and over here we only have only x's and a dx. And the idea now is you're going to integrate both sides, but before we do that, let's see, let's put this y into, is 1 over the square root of y is y to the negative 1/2. Okay, and now what we do is we integrate both sides of the equation separately. Okay, so the integral of this would be, let's see, we raise this by 1. So negative 1/2 plus 1 is positive 1/2. And then, let's see, if we take the derivative here, then that will be reduced by 1. But then we'll also have this 1/2 coming out. So we'll put a 2 there to counter that. And then over here, x squared. So that'd be 7 x squared over 2. And then you put a constant. Now, technically, both sides are going to have a constant, but it's the same as if you just put on one side, because, you know, if you had a constant here and a constant there, then you could just take this constant and subtract that constant from it, and you get a new constant. That's the kind of the idea right there. And so that is it. That's you can just leave the equation like that. Two y to the 1/2 equals 7x squared over 2 plus c. Okay, or you could, I guess, maybe it's better to put it like this. Maybe it's better to write the instead of y to the 1/2, write the square root of y. This will for sure work. And if you want, you could go a step further and try to solve for y. But that's not necessarily what we need to do here. We don't need to have it implicit. We don't need to have it explicitly defined. Implicitly defined is okay. Okay, any questions about that before we move on? Okay, let's do another one. This is going to be more of the same. So this differential equation. So here we have du dt. And so again, treat this as a fraction. Let's see, let's do this first. So the numerator is 6 plus 2 to the 4th, and the denominator is t squared times u plus u to the 4th. Okay, so yeah, so we're gonna split it up like that. So we're able to factor a t squared out of the denominator. Now you treat this as a fraction. get all the u's over here and all the t's over here. So this comes over here to the numerator. And over here, we're left with this. Okay, now let's put the right-hand side into a better way, into a better form that we can integrate. This is the same as 6 over t squared. That's 6t to the negative 2. And then t to the 4th over t squared is t squared. And then, of course, at this stage, we integrate both sides. Again, the nice thing is that you could, because this plus is in the numerator, you can split it up into 2 pieces, this over this plus that over that. Okay, so integrating this, we have u squared over 2, and then this is u to the 5th over 5 over here. And then over here, we have, let's see, if you raise this by 1, that's t to the minus 1, so that's negative 6. The derivative of that, negative 1 will come down, and so you get a 6, and then that's reduced by 1 to negative. So that's fine. And then t cubed over 3. And then you add a constant there. Okay, so we have u squared over 2 plus u to the 5th over 5 equals negative 6 over t plus t cubed over 3 plus a constant. So number 3, solve the differential equation that satisfies the given initial. So here they're putting an initial condition in there. And this right here basically means when you have an initial condition, that means find the constant. Okay, you use that to find the constant, but you don't really use it to solve it. Okay, so anyways, let's go ahead and solve this one. So again, you treat this as a fraction. You have u there, and you have t's in the numerator. So all u's in the denominator, all t's in the numerator. So that's great. So that means we can take this 2u over to the left-hand side. It goes from denominator to numerator. And we take the dt over to the right-hand side. Okay, and then you're going to integrate each side separately. And so over here we have u squared, because the derivative of u squared is 2u. And then over here, we integrate each of these. So this is t squared. And the integral of secant squared is tangent. Oops. And then you add a constant on the end like that. Okay, so this means find the constant. And what you're going to do is you're going to set u equal to negative 5. So that's right here. That u gets set equal to negative 5. And t equal to 0. Okay, so you're going to set those t's equal to 0 here, because this is usually u of t is what your function is, u of t. Okay, so this is going to be 0 squared plus tangent of 0 plus a constant. And of course, these are both 0. So this is 25, and this is our constant. So our constant is 25. And what you're going to do is you're going to take that 25, and that is going to go in to here. Okay, so we have, I need more space actually, hold on. Okay, so that gives you u squared equals t squared plus tangent t plus a constant. Okay, now, here, they actually want you to go further and not just leave it like this. So if you extract square roots, then what you're going to get is this. Oh, wait, what am I doing? I did that whole thing just to say, you know, C was going to be 25, right? So that's a 25 right there. Okay, so this C is 25, so replace this. Basically, the idea was to replace this C with the 25. Okay, and that's completing this part, find the constant. Find the constant, and then put it back into the equation. So you have the equation here. And they want you to go a step further, and so here, you extract square roots, you get this. But because, and this is a little bit tricky, because this is a -5, that means that over here, you get, it's going to be the minus is what you're going to look at. Negative, the square root of t squared plus tangent t plus 25. Okay, so because we know the initial condition, then we can go further. Okay, so so u of 0 is negative. So in other words, if you were to plug a 0 in for t, this part here, the square root of 25, would be 5. But according to this, it could either be plus or minus according to this, but it has to be minus. So you have to have the minus. It has to be the minus one. Okay. Because the square root, this symbol here, we say square root, but what it really is the positive square root. It's only referring to the positive square root. That's what this symbol is. Okay. Any questions about that? Or anything that we've done so far?
So first, can you explain why, like, it has to be negative?
Yeah. Because this initial condition, when you plug a 0 in for t, when t is 0, u has to be -5. Okay, and so it can't be +5. So that you have to get rid of the positive. It has to be negative.
Then, like, can we plug in something else, like maybe like 2 or 4?
If you plug a 2 in.
Yeah.
Well, yeah. Well. It could. But that's kind of irrelevant to the thing. Let me think. This right here, when you have a plus or minus, it's showing these are two different curves. If it's a plus or a minus, are two different curves. So the plus might be something like, I mean, this is not going what it's going to be, but the plus could be something like this, like a curve like that, and the minus could be a curve like this. Okay, there's nothing in relation to that. But you put this condition right here. This right here is a point that's on the minus curve. Okay, so if that point is if you have this initial condition says you have to go through your curve has to go through that point right there. Okay, so that means it's got to be this curve, not this curve, because your curve has to go through that point. Okay, it has to go through the point that corresponds to the minus 5. Okay, so does that make sense? So it has to be this one. Or the solution curve has to go through, but this point. So that means that yellow curve has to be the curve, that has to be the solution. Okay. Let's move on to number 4. I mean, again, this is not any resemblance to what this is or anything. I'm just saying that this plus or minus gives you 2 different curves, and the point has to go through, you want the curve that goes through that point, and it's going to be the minus curve, not the plus curve.
Oh, okay, thank you.
Sure. Okay, so let's look at number 4. Solve the differential equation that satisfies the initial condition. So again, we have this initial condition right here. And here's our differential equation. Now we have capital L and T are the variables. L is the unknown function, T is the variable. So again, let's see here. We can separate this. And you get that. Let me write this as negative L to the negative 2 dt equals K log T dt. Okay, so now what we're going to do is we're going to go ahead and integrate this. Integrate each side separately. If you add 1 to this, you get minus 1. But you take your derivative, you have a minus 1 coming down. So, and then this is L to the minus 2. Okay, over here, this one you can do by integration by parts. Let me do that over here. We're going to use integration by parts. Okay, so you remember the thing that we had right here. So the logarithm is the first choice for our u usually. if like you're splitting up in certain ways, and then let's see, du will be dt over t. Okay, and then dv we'll let that be k dt, so that v is kt. Okay, great. So now we plug everything in. uv, that's log t. Okay, u times v, so that's times k dt, times kt. So I'm going to go ahead and put that over here. Kt log t minus the integral of v du. So that would be this times that. Oh, that's great. That's going to be kt times dt over t. And that's just the integral of k dt. And integrate that, you're going to get kt. And then we put a constant on the end. Okay, so great. We come down to here. And essentially, this is the same as negative 1 over L. Okay, so if I take reciprocal of both sides, then I'm going to get negative L. The reciprocal of this is just negative L, and the reciprocal of this is 1 over KT log T minus KT plus C. Or I'll take the negative over here at the same while I'm at it, okay? So I don't want to rewrite this all again. So I took the negative over there, sorry about that. Okay, and now what you want to do is plug in this initial condition right here. Make L negative 6 and make T equal to 1 in that equation. Okay, so L equals negative 6 and T is 1. Okay, so this becomes negative 6 equals, and then we have negative 1 over here. And then T is 1, so I put a 1 in here. K times 1 times log of 1 minus K times 1 plus C. The negatives are going to reduce. Now, let's see here. Log of 1 is 0. That goes away. Okay, so we get what we need to do is solve this for C. Okay, so initial condition means solve for the constant, solve for this C right here. Okay, so take the reciprocal of both sides. And you're going to get C is K plus 1/6. Okay, so what you're going to do is you're going to plug that into here. So this this gets replaced by that K plus 1/6. And so this would be the answer right here. You can also factor out each of the this and this and this has K's in it. So you could factor a K out all the way out of that if you want. And that should work out as the answer. Any questions or comments about that one? Okay, let's move on to the next exercise. Okay, so the fifth and final exercise of the assignment, you have a tank that contains 6,000 liters of brine. And this is basically just water mixed with salt, as far as what I'm understanding. So 6,000 liters of brine, so it's 4 kilograms of salt in there. Pure water enters the tank at the rate of 60 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. Okay, so this right here or in particular this right here. Sorry. Hold on. Let me start over. Okay, so what we're going to do is we're going to let x of t equal the amount of salt in the tank at time t. Okay, so because the first question is how much salt is in the tank after t minutes. So this is going to be x. So x is going to be, this will be the answer. This is the amount of salt in the tank at time t. Okay, now initially, when you start out, you have 14 grams. X is 14. This amount is 14 when you start out when time is 0. Okay. Oh, and then t is also going to be in minutes because these are minutes. These are both in minutes. Okay. Okay, now let's look and see what's going on. So pure water enters the tank at the rate of 60 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. Okay, so incoming, the amount of salt that's coming in is, okay, so pure water is coming in, so there's no salt in that. Okay, and then you have leaving salt that's just leaving the tank, being drained out. It's the amount of salt per liter. Let me think. So okay, so X is the amount of salt in the tank, then the amount of salt per liter, is X over 6,000. Okay, that's the amount of salt per liter. So you're multiplying by salt per liter times the number of liters that's leaving. Okay, you have this many liters per minute that's leaving the tank, and this is how much salt per liter that there is. So you have it's X over 100. Okay, so what this information allows us to do is come up with a differential equation. So the change in salt over time is equal to the amount that's coming in minus the amount that's going out. Okay, so the change in salt per time is the amount that's coming in, that's incoming, minus outgoing. Okay, so incoming and leaving. This amount coming in, this amount's leaving. Okay, so dx dt is negative x over 100. And this is a separable equation. You don't have any t's over here though, so you're like, whoa, no t's. But that's okay. We're still going to do the same thing as we did before. We're going to get all the x's over here, all the t's over here, even though there are no t's, but we'll get the dt over there. Okay, so dx over x, we'll pull this x over here, and then negative 1 over 100 dt. Okay, so we've separated into all the dx's, all the dx and all the x's over here. The dt's over here. There's no t's, so we're fine. And now, of course, you integrate. And this left-hand side is log of x. And the right-hand side is negative 1 over 100 t plus a constant. Okay, so now what we're going to do now is we're going to exponentiate both sides. And by that, we mean basically take each side, e to this side equals e to that side. But e to this side is just x. Okay, now, if you look at this right here, this is e to this plus that plus that. Okay, negative t over 100 plus c. It's the same as e to this times e to that, e to the c. So, and then e to the c is just another constant. So I don't have very much space here, but I'm going to, in other words, this right here, we could have just written it like that. And then what typically would happen in this case is, well, let me just continue on, okay? Let's evaluate the initial condition, okay? So here we have the initial condition. Okay, x is 14 when t is 0, okay? And we'll put that into here. So 14 and make that t equal to 0. This is just going to be 1. So really you have e to the c is 14. And instead of finding c, c is the natural log of 14 and then plugging that into here, we found e to the c is 14. So I just replace this e to the c with a 14. And that's the answer to the first part, okay? Namely, it would be just this piece. Okay, so you just put in this 14 e to the negative 1 over 100 t. Okay. And then that's for part A. And then for part B, how much salt is in the tank after 20 minutes? You set t equal to 20. So the answer will be 14 e to the negative 1 over 100 times 20. So replace that t with a 20. Okay, and I used the calculator and I got 11.462, so on, so on, so on. So, but it says round to 1 decimal place, so 11.5. 11.5 kilograms of salt is left in the tank. Okay, so just a quick note in closing about this problem, and that is when you have this kind of a situation, you'll notice that this is actually, this e to the c is 14. This is actually the initial amount, okay? So this is typically referred to as x0, okay? And so, in other words, your equation would be x equals x0 e to the negative 1 over 100 t. Okay, and that's like the initial amount, because that's the initial amount, okay? It's the initial amount. it's 14, and it turned out to be 14 in this case, but sometimes they don't give it to you. So you can just like, so that's typically how people would denote this.